we are moving into, in lesson 11.1, we're going to be dealing of a linear system. And a couple of things I want you to recall written on the Cartesian plane in the form x, y, with strung together, okay? That makes the equation true. So here we have a couple examples we're going to go over later, make this statement true. Okay, so that's just recalling from lines in general. All right, so at the beginning of lesson 11.1, where it begins on page equations or a linear system, or linear equations that have the same variables. That just means equations are going to have an x and a y. And one linear equation, this is another set notation before we have a list of things, but then there's one closing it out. When we want to consider two linear equations together as a system, we link them with this curly bracket. And so whereas just graph crosses another line or is parallel to another line, right? And if they're parallel, they don't cross anywhere. So recall all the points that make this line true. So when they cross, the point where two lines cross is one point with coordinates x, y, and that x and that y will satisfy both equations in the system. And that's what we're going to talk about more today, okay? So the solution of a linear system with two variables is any ordered pair that satisfies all of the equations in the system. So here we're dealing with systems of two equations. I think that's all we're going to do in Algebra 1, but you can have systems of more than two in the system. And again, that comes from page 479 in your book. So we're looking now, whereas before we were just graphing. So first we want to begin by pointing out black lines are my axes, these blue lines are my lines from the system, and they intersect at this one point. And this type of system is called a consistent independent system. Okay? It's consistent. Okay? The next one we have is here, and I drew this line our system. And so there's another situation. An example might be x plus y equals 10, or in this case, the 2 points. Okay? This is called a consistent dependent system. That means that they intersect at infinitely many points, and it's called a consistent dependent system. Okay, intersect. They intersect at 0 places. So they have no points of intersection. Okay? They will never touch, they will never intersect. This is called an inconsistent system. When they intersect at infinitely many points. Then we have a consistent independent system where the two lines intersect at exactly 1 point. So those are our three kinds of intersections. System looks like by graphing. Okay? Number 3 on page 481. Okay, number 3 on page 481. And I've written the two lines in different colors, the two equations in different colors, because we're going to graph them, and we want to be able to tell the lines apart. Okay? Because we're going to graph them and see where they intersect. So I'm going to come over here. I'm going to know that I'm at y-intercept, -2. And I have a slope of -2, which means I either go down 2, right 1, or up. And I'm going to graph the black line. And I might want to continue this actually. Let's see. Okay, now, so I've graphed the first line. Now I want to graph the second line. This is in standard form, so it might be easier to plot the intercepts and then connect them. So when x is 0, y is 1. So when x is 0, y is 1. That means I have a y-intercept of 1. And when y is 0, x is 2. So I have an x-intercept of 2. Okay? So now I will connect those 2 points to graph my blue line. Cool, so now I have a black line here and a blue line here, okay? And I see that I have a consistent independent system. They intersect at exactly 1 point. And it looks like, now I didn't graph it perfect, so my intersection isn't right on this point, but I think it's negative 2, 2. So left 2, up 2, negative 2, 2. So I think that my point of intersection is negative 2, 2. Now remember, the solution to a system of equations is the ordered pair that satisfies both equations. So I can check this by plugging in those values to both equations and making sure it satisfies both. So I'm going to do that. I'm going to take negative 2, 2 and plug it into the black equation. Okay? So I'm going to plug in negative 2 for x and 2 for y. So I have y is 2 equals negative 2 times x, which is negative 2, minus 2. So that equals 2 equals 4 minus 2. 2 equals 2. Check. It satisfies the black equation. Okay? And then I'm going to check the second one. So I have x is 2 plus 2 times y, which is, x is negative 2 plus 2 times y, which is 2, equals 2. Okay? So negative 2 plus 4 equals 2. Sure enough, negative 2 plus 4 is 2 equals 2. Check. So negative 2, 2 works for both. That means I graphed it properly, and I was able to interpret my graph well to see where the two lines intersect. Okay? And I got this point, I plugged it back in. Sure enough, this point satisfies both equations. So I found the solution to the system. It is the point negative 2, 2. Okay? So now on that same page, 481, I want you to try number 4. Number 4 says, the system is y equals 2x plus 8. Okay? And the second equation is negative x plus y equals 6. Okay? And I want you to find a point and then check it. Okay? The point you should get is negative 2, 4. Points. When you do, I want you to plug in sizes when we're together the next time in class. Happy mathing.